Step one, by counting our valence electrons here, what has to happen with that -1 charge?
It has to go on the outside.
Okay, we will put it on the outside, but what happens when we count our valence electrons? We have to add one more electron, right? That negative charge tells us we have an extra electron. So if I'm going to count my valence electrons here, we feel comfortable with how many? Carbon gives us how many? 4, and there are 2 of them, plus 3 from hydrogen, plus 2 times, how many does oxygen give us? 6, plus that extra one, okay? We're comfortable with our valence electrons follow the group numbers, right? We're good with that trend, all right. So I'm going to add up all of those valence electrons. That gives me 8, 11, 23, 24 electrons. Can I do math in my head? Okay. So 24 electrons. Then we're going to build our skeleton. Okay, so what has to go in the middle?
Carbon.
It's got to be carbon. In this case, we have how many central atoms?
2.
We're going to end up having 2. Can hydrogen ever be a central atom?
No.
No, and why not?
Wait, because it can only have one.
And that leads me to only one bond, right? Hydrogen only ever gets one bond. That's it, right? It only contributes one valence electron. So it can't have more than that. Okay, so let's put carbon in the middle here. 2 carbons. I'm going to change my color here. 2 carbons and the 3 hydrogens. And then oxygen, oxygen. Okay? C2H3O2. Another way that acetone is written, let's remember this. We said acetone could also be written like this. CH3COO minus. This form, writing it this way, gives us a way bigger clue about our skeleton. You see what that means? CH3COO. Right? So it gives us a little bit more of a clue as to our skeleton. So that's why it's written that way. These mean the same, right? 2 carbons, 2 oxygens, 3 hydrogen, right? But that gives us a better clue about our skeleton. Okay? Acetone is really one of the only ones that gets, alternate writing like that, but I don't know. Okay, so we've got our skeleton built. Now we're going to bond our atoms. So we're going to bond 2, 4, 6, 8, 10, 12 electrons I've used. So that means I have 12 electrons left to represent in my structure. Okay? So that means I'm going to put them out here. 2, 4, 6, 8, 10, 12. Why would I not start putting them around hydrogen? Hydrogen never gets lone pairs, right? Oh, I should have asked you what those are called. Would you have remembered what these are called? Obviously lone pairs. Okay, yes, obviously you would have remembered that. Okay, hydrogen's never going to get lone pairs. It's only going to get a bond, okay? So tell me, does this look like a complete Lewis structure?
Yeah.
Oh,
the dipole moment.
No.
double bond. I feel like we need something on that carbon.
I think we need something on this carbon too. Look, because carbon's octet's not full, is it? 2, 4, 6. So can I double bond here?
Yeah.
No.
Oh, no.
No, because first of all, the problem is I brought 2 electrons out of nowhere. So that's no good. So I need to relocate 2 electrons. Take a lone pair, double bond. Very nice. But here's the thing, how do I choose which oxygen to do that? Flip a coin. Yeah, that's how it works. Okay, I'm going to take a lone pair, put a double bond. Should I do that for both oxygens? Then carbon has too many. Carbon's not allowed an expanded octet. So that's no good. So now what? Is this it? This is a trick question. Okay, yes. There is a couple more things. Man, I picked a good example without really even thinking about it. Okay, is this the only way that this molecule can exist?
No, we need
those guys.
Yep, those guys.
the
They're like
Resonance structures. Very nice. We need a resonance structure. And remember, what is a resonance structure?
it's like possible bonds.
Yeah, other possibilities, right? Really, resonance.
I remember seeing resonance.
Yeah, not a Renaissance structure. Okay, so here's my other structure. Except what I'm going to do with it is change that double bond, right? I'm going to represent the double bond with the other oxygen. So I'm going to get rid of that one. I'm going to remove that lone pair, and I'm going to change my double bond, right? So those two are now resonance structures, right?
And then we have to put them in the brackets.
Yes, good. Yep, what has to go between them?
The double arrow.
Double-headed arrow has to go in brackets, right? What's that double-headed arrow tell us? It tells us that we're representing the same molecule, right? That those two things are the same. Okay, now we've got one more thing we've got to put.
The negative one.
Negative one charge has to go out there. We feel like pros? Lewis structure pros?
Yeah.
Okay, now I want to talk one thing about resonance structures. In Chem 1, we gave a small definition or a broad definition of resonance structures. And although we said these are the multiple ways that this atom can be represented, in reality, a resonance is an average of these two things, right? And these electrons really almost float between these two bonds. And the true structure of acetone is like an average of those two. So we represent both so that we can see them, but the real one is a smush between those. Would you agree, Mr. Moritz? Let's figure out, where is this -1 charge located within my atom? Right? Let's just look at this one on its own. That -1 charge has to be held by an atom, right? If I'm looking at just this structure, where is my -1 charge found? Is it on carbon, hydrogen, hydrogen, carbon, oxygen, or oxygen? Oxygen. And which one?
The one with more lone pairs.
Yeah, very good. Okay, so let's figure out, why does this oxygen have a formal charge? Right, so tell me. That's right. It contributes how many to the structure? It contributes only 6. It only contributes 6, but directly next to it, it has 1, 2, 3, 4, 5, 6, and 7. Right? And so there's where that -1 charge comes from. Okay, so if I'm looking at just this picture, this would have that -1 charge. But the reason we put it outside is because if we're talking about a true resonance here, right? If we're talking about a true average, right? That -1 charge kind of floats between those. Okay, so that's why we put it outside the brackets. But we do need to be able to assign them for molecules that don't have resonance or whatever. We need to still be able to assign formal charges. Okay? All right, do you remember when we talked about likes or dislikes for the atoms? Remember I had that chart up here for Chem 1, right? What does carbon like to have? Okay, let's put that up here. Do you want to put that in your notes, or do you feel comfortable with that? Okay, I'm going to put it up there just in case you want to see it, okay? So this would be the group. This would be the number of bonds. This would be the number of lone pairs. I used my line tool. I'm not that good. All right, so if I look at carbon's group likes to have, it has 4 valence electrons. So what does it like to have? 4 bonds, no lone pairs. Move over to nitrogen's group. It likes to have 3 bonds, 1 lone pair. Oxygen's group likes to have 2 bonds, 2 lone pairs. Fluorine's group likes to have 1 bond, 3 lone pairs. And then neon's group likes to have no bonds and 4 lone pairs, right? It doesn't want to. It doesn't want to bond. Okay? Because let's think about this. Fluorine contributes 7 valence electrons. So one of them is near it with the bond, plus these 6, right? The 6 that are contained in the lone pairs. Oxygen has 2 near it from the bonds, and then 4 near it from the lone pairs. So that would give us 6 total, right? These are preferences for atoms. And so when at all possible, we want to try to get atoms and Lewis structures sorted out to meet those preferences, because that would give them a neutral, right? The point of a Lewis structure and the point of a ground state or low energy Lewis structure is to eliminate as many formal charges as we can. Okay, so let me say that again, as many formal charges as we can. If I was going to do you guys, are you good with this one?
Yeah.
Do you have that up? If I was going to do a Lewis structure for sulfate, SO4 minus 2, I could go, let's see, that's 6 times 5, so that would be 32 electrons. I could do this. and fill in my lone pairs. Right? And that would be a valid Lewis structure. Would you agree? All the octets are full, like we're good. But here's the problem. What charge do each of those oxygens carry? They all would have a -1 charge. And what charge would sulfur carry? Plus 2, right? It contributes 6, but it has 1, 2, 3, 4 directly around it. Now, all of my atoms have formal charges, which could be valid, but it's uncomfortable, right? So our goal is to get that Lewis structure to the lowest energy possible. And so what I would do there, do you have any ideas? Good. So I'm going to double bond any 2 of those oxygens, right? I'm going to take away charges. And by making that a double bond, now I've eliminated the charge on sulfur. I've eliminated the charge on those 2 oxygens. And so here's where my -2 charge comes from, right? Now only 2 of my oxygens are carrying charges.
Wait, how do you know that sulfur has a plus charge?
Because sulfur contributes 6, right? And around that 1, 2, 3, 4 would only be 4. Okay, does that make sense? So by adding those double bonds, yes, it violates the octet rule for sulfur, but it eliminates formal charges, which is more important than the octet rule. Does that make sense? So formal charge kind of trumps the octet rule in order of importance. And then this one would need how many resonance structures? Several, right? You have to show this one, this one, this one, this one, right? You have to show 4 different numbers. That can make sense. So that means all of those bonds are really like 1.5, right? That would be in real life, they would all kind of end up as 1.5. Does that make a little bit more sense? Is that bringing big picture things together? Okay, very good. I'm going to stop us there.